This shows the measurement frequency and interval for valves controlling volatile organic chemicals, VOC.
I will now discuss how the criteria for selecting packing systems have evolved. In the past, the choice of which valve stem packing to use was primarily determined by the operating temperature in the packing box area. The options were simple. PTFE was used for temperatures below 93 degrees Celsius or 200 degrees Fahrenheit, and graphite was used for higher temperature applications. However, today, selecting a valve packing system has become much more complex due to several considerations. For example, emission control requirements imposed by the Clean Air Act in the US and other regulatory bodies place tighter restrictions on sealing performance. Additionally, constant demands to improve process output mean that the packing system must not hinder valve performance. Furthermore, today's trend toward extending maintenance schedules requires packing systems to maintain the required sealing performance over longer periods. Given the wide variety of applications and service conditions in industrial sites, the selection process has become that much more challenging.
Finally, I'd like to introduce how packing is evaluated and compared, and cover the first specific type of packing. As seen in Figure 3.22, variables such as sealing ability, operating friction levels, and operating life are difficult to quantify and compare due to the diversity of industrial sites. Therefore, the following tables provide a relative evaluation of packing applicability and performance using an engineered approach. However, to properly interpret these tables, a clarification of trade names is first required. First, the single PTFE veering packing shown in Figure 3.23 uses a coil spring between the packing and the packing follower. This configuration meets the 100 ppmv criteria, provided that the pressure does not exceed 20.7 bar, 300 psi, and the temperature is between -18 and 93 degrees Celsius, 0 and 200 degrees Fahrenheit. It offers very good sealing performance along with the lowest operating friction. Now let's introduce the EnviroSeal PTFE packing system. Following the single PTFE veering packing in Figure 3.23, you can think of this as a more advanced packing method. The core of this system is a compact, live-load spring design. Since the spring continuously applies a constant load to the packing, the sealing performance is well maintained over time. In terms of application range, it is suitable for environmental applications up to a pressure of 51.7 bar and a temperature of 232 degrees Celsius, which is 750 psi and 450 degrees Fahrenheit. While it is commonly thought of as an emission-reducing packing system, please remember that it can also be sufficiently used in general processes unrelated to environmental regulations. You can check the detailed structure in Figure 3.24.
This is the configuration of the PTFE packing system with EnviroSeal technology applied.
Next, I will introduce high-performance packing systems for environmental regulation compliance. First, EnviroSeal duplex packing combines the advantages of both PTFE and graphite components, providing a solution that is low in both friction and emissions and has passed the API standard 641 fire test. It can be applied to process temperatures up to 232 degrees Celsius or 450 degrees Fahrenheit. Next is CalRes packing. Please note that the pressure and temperature limits presented here for CalRes are based on Fisher valve applications. When CalRes is combined with PTFE, it is suitable for environmental use up to 24.1 bar, 350 sig, and 204 degrees Celsius, 400 degrees Fahrenheit, and can be used in some non-environmental services up to 103 bar, 1500 sig. Additionally, when CalRes is combined with Zymax, which is a carbon fiber reinforced TFE, it can withstand service up to 260 degrees Celsius, 500 degrees Fahrenheit.
This is the EnviroSeal duplex packing system, which is a mixture of PTFE and graphite.
I'd like to introduce the graphite packing system for high-temperature environments. The EnviroSeal graphite ULF packing is primarily designed for environmental applications at temperatures exceeding 232 degrees Celsius, 450 degrees Fahrenheit. The patented ULF structure is characterized by the placement of very thin PTFE layers inside the packing rings, as well as thin PTFE washers on each side of the packing rings. Strategically placing PTFE in this way minimizes control problems and friction, enhances sealing performance, and extends the cycle life of the packing set. Meanwhile, the high-seal graphite ULF system is identical to the EnviroSeal graphite ULF below the packing follower, but differs in its use of heavy-duty, large-diameter Belleville springs. These springs provide additional follower travel, and if calibrated with a load scale, the packing load and wear status can be visually verified.
This is the EnviroSeal graphite packing system with ultra-low leakage, ULF characteristics.
This chunk corresponds to the PTFE carbon/PTFE packing set label shown in the packing cross-sectional drawing. This configuration refers to a packing set that uses pure PTFE rings and carbon-filled PTFE rings together. Carbon filling reinforces the strength of the ring and its resistance to extrusion, resulting in higher operating stability than when using pure PTFE alone. At the same time, the low friction characteristics unique to the PTFE family are maintained. These sets are provided as one of the packing box configuration options for globe-type valve bodies, along with graphite packing arrangements.
This chunk corresponds to the drawing labels indicating the internal components of the packing box. The parts shown are the lantern ring, graphite packing rings, and the packing box ring. The lantern ring is a component located in the middle of the packing stack. It connects to a port drilled into the side of the bonnet and serves as a passage for purging, lubrication, or detecting leakage from the first packing set. Graphite packing rings are key sealing elements that block leakage even in high-temperature and high-radiation environments, and the packing box ring supports the bottom of the stack and maintains alignment. The drawing also includes identification codes such as 24B9310, a 6844/IL, and 39B4612A.
I would like to introduce the environmental packing for rotary valves and the performance comparison table. The drawing presents the EnviroSeal duplex, graphite ULF, and graphite packing systems for rotary valves, which maintain a constant packing stress through a spring pack assembly, bushing, and packing washer. The EnviroSeal graphite packing for rotary valves is designed for environmental applications from -6 degrees Celsius to 316 degrees Celsius, or 20 degrees Fahrenheit to 600 degrees Fahrenheit, or for applications where fire safety is a concern. It can be used with pressures up to 103 bar, or 1,500 psi, while still satisfying the 500 ppm EPA leakage criteria. Meanwhile, the graphite ribbon packing for rotary valves is for non-environmental use, covering a wide temperature range from -198 degrees Celsius to 538 degrees Celsius, or -325 degrees Fahrenheit to 1,000 degrees Fahrenheit. The following performance comparison table lists the maximum pressure and temperature for 500 ppm service, the seal performance index, and packing friction. The first row, single PTFE V-ring, starts at 300 psi, from 0 to 200 degrees Fahrenheit.
This is the EnviroSeal graphite packing system optimized for rotary valves.
Now, I would like to introduce the EnviroSeal PTFE item from the sliding stem environmental packing selection table. This packing system refers to the item in Figure 3.25, and its temperature application range is specified from -50 degrees Fahrenheit to 450 degrees Fahrenheit. In metric units, this corresponds approximately to the range from -46 degrees Celsius to 232 degrees Celsius. This table is structured to compare each packing system across horizontal items, such as maximum pressure and temperature limits for 500 ppm, seal performance index, service life index, and packing friction grade. EnviroSeal PTFE uses a PTFE-based live load spring structure to reduce environmental leakage.
Next, I will introduce the EnviroSeal duplex item in the environmental packing selection table. Duplex is a composite configuration using both PTFE and graphite. The maximum pressure limit specified in the table is 750 psi, and the temperature application range is from -50 degrees Fahrenheit to 450 degrees Fahrenheit. This configuration combines the low friction characteristics of PTFE with the heat resistance of graphite to provide a solution with low friction and low emissions. It has also passed the API standard 589 fire test and is applied to uses up to a process temperature of 232 degrees Celsius or 450 degrees Fahrenheit.
I will now provide a detailed introduction to the overall structure and key notes of the sliding stem environmental packing selection table. First, the EnviroSeal graphite ULF item is listed with a pressure of 1,500 psi and a temperature from 20 degrees Fahrenheit to 600 degrees Fahrenheit. Note 1 in the table is very important. It states that the values presented here are guidelines only, and while they can be exceeded, it may result in shortened packing life or increased leakage. It also clarifies that temperature ratings apply to the actual packing temperature, not the process temperature. For non-environmental applications, graphite ribbon packing covers a wide temperature range from -325 degrees Fahrenheit to 1,000 degrees Fahrenheit, or -198 degrees Celsius to 538 degrees Celsius. However, the table clearly distinguishes that braided graphite filament and double PTFE are not acceptable environmental sealing solutions. This table uses pressure and temperature limits, seal performance index, service life index, and packing friction as comparison axes. For example, the single PTFE veering is rated at 20.7 bar, from -18 degrees Celsius to 93 degrees Celsius, with a seal performance of better, service life of long, and friction of very low.
This screen introduces the performance comparison data rows for the EnviroSeal series in the sliding stem environmental packing selection table. The EnviroSeal PTFE, corresponding to Figure 3.25, is rated as superior for seal performance, very long for service life, and low for friction in the range of -46 degrees Celsius to 232 degrees Celsius. The item with a pressure of 51.7 bar in the same temperature range is also rated as superior, very long, and low. The EnviroSeal graphite ULF, with a pressure of 103 bar and a temperature from -7 degrees Celsius to 315 degrees Celsius, has the same superior and very long ratings for performance and life, but the friction is one level higher at moderate. In other words, the superior grade is better than the better grade, and all EnviroSeal series are assigned a very long service life. The drawing codes listed in the table are W0959/IL, W0958/IL, and W0957/IL.
Now, I will introduce the structure of the packing selection table applied to rotary valves. Unlike sliding stem valves, it is first specified that single PTFE and graphite ribbon packing arrangements do not perform well as environmental sealing solutions for rotary valves. This table also uses the maximum pressure and temperature limits for 500 ppm, seal performance index, packing system, and packing friction as comparison axes. The units are presented using both the US customary and metric systems.
Finally, I will introduce the EnviroSeal PTFE item in the rotary valve packing selection table. The maximum pressure limit for this item is 1,500 sig, and the temperature application range is from -50 degrees Fahrenheit to 450 degrees Fahrenheit. Note that sig indicates the notation is based on gauge pressure. Unlike the single PTFE or graphite ribbon arrangements for rotary valves seen previously, the EnviroSeal series is presented in the table as the recommended solution for environmental use in rotary valves.
Next, we turn to flow characteristics.
I'd like to introduce the EnviroSeal graphite packing and the flow characterization of cage-guided valves. First, the 500 ppm service limits for this packing system are 1,500 sig and 20 to 600 degrees Fahrenheit. The values shown in the table are guidelines only. They can be exceeded, but doing so may result in shortened packing life or increased leakage. One point to note is that these temperature ratings apply to the actual packing temperature, not the process temperature. Through these stem sealing technologies, fugitive emissions from valves can be controlled, while simultaneously reducing the industry's cost of regulatory compliance. Although EnviroSeal packing was originally designed for fugitive emission applications, these technologies should also be considered for any application where seal performance, seal life, or maintenance costs have been an ongoing concern. Moving on to the characterization of cage-guided trim, the key is that the shape of the flow openings or windows in the wall of the cylindrical cage determines the valve's flow characteristics.
I will continue by explaining how the shape of the cage windows creates flow characteristics. First, in the case of rotary valves, single PTFE and graphite ribbon arrangements do not perform well as fugitive emission sealing solutions. Looking at the rotary environmental packing selection, under conditions of 13 bar and -46 to 232 degrees Celsius, the seal performance is superior, service life is very long, and friction is low. In another condition of 13 bar and -18 to 315 degrees Celsius, the seal performance is superior and service life is very long, but friction is moderate. Returning to the operating principle, as the valve plug moves away from the seat ring, the cage windows open to create a flow path through the valve. Standard cages are designed to produce three inherent flow characteristics: linear, equal percentage, and quick opening. You can see that the cage windows in Figure 3.28 have different shapes. The flow rate/travel relationship provided by these cages is equivalent to the linear, quick opening, and equal percentage curves shown for contoured plugs in Figure 3.29.
These are the various characterized cages used in globe-style valve bodies.
This is the detailed structure of the cage that determines the flow characteristics of a globe-style valve.
These are cages for globe valves designed according to flow control characteristics.
These are the inherent flow characteristics curves according to the valve travel.
I'll now introduce the maintenance advantages of cage-guided trim. Cage-guided trim offers a distinct advantage over conventional valve body assemblies. The most significant point is that the maintenance and replacement of internal parts are much simplified. Additionally, the inherent flow characteristic of a valve can be easily changed simply by installing a different cage, allowing for flexible responses even if operational requirements change.
I will continue by explaining how to change characteristics via cage interchange and discussing specialized cages. A major advantage is that when changing the inherent flow characteristic by replacing the cage, there is no need to change the valve plug or seat ring. The standard cages shown in Figure 3.29 can be used with either balanced or unbalanced trim constructions. If soft seating is required, it is provided as a retained insert in the seat ring, which is independent of the cage or valve plug selection. Cage interchangeability can be extended to specialized cage designs that provide noise attenuation or combat cavitation. However, these specialized cages provide a modified linear inherent characteristic and require the flow to be in a specific direction through the cage openings. Therefore, it may be necessary to reverse the valve body in the pipeline to obtain the proper flow direction.
I would like to introduce characterized valve plugs. The valve plug is the movable part of a globe-style control valve assembly, creating a variable restriction to fluid flow. Each plug style is designed to provide a specific flow characteristic, a specified manner of guiding or alignment with the seat ring, or a particular shutoff or damage resistance capability. Plugs are designed for two types of control. First, two-position control, where the actuator positions the plug at one of 2 points within the travel range. And second, throttling control, where the plug can be positioned at any point within the travel range as dictated by process requirements. The contour of the plug surface next to the seat ring is the key factor that determines the inherent flow characteristic of these globe-style valves.
I will explain the definition of inherent flow characteristics and linear characteristics. As the actuator moves the plug within its travel range, the size and shape of the unobstructed flow area change depending on the contour of the plug. When a constant differential pressure is maintained across the valve, the changing relationship between the percentage of maximum flow capacity and the percentage of total travel range can be plotted, and this is the inherent flow characteristic of the valve shown in Figure 3.29. The first of the commonly specified characteristics is the linear characteristic. A valve with an ideal linear inherent characteristic produces a flow rate directly proportional to the plug travel throughout the travel range. For example, at 50% of rated travel, 50% of the maximum flow rate occurs, and at 80% travel, 80% of the maximum flow rate occurs. In other words, the rate of change in flow rate relative to plug travel remains constant, which is why linear characteristic valves are often specified for liquid level control or flow control applications requiring a constant gain.
I would like to introduce the linear and equal percentage characteristics among the inherent flow characteristics. In a linear characteristic, the flow rate is directly proportional to the travel of the valve plug. For example, at 50% of the rated travel, 50% of the maximum flow rate occurs, and at 80% travel, 80% of the maximum flow rate occurs. That is, the rate of change in flow rate relative to plug travel is always kept constant, which is called a constant gain. Due to this constant gain characteristic, linear characteristic valves are frequently specified for liquid level control or flow control applications that require a constant gain. The equal percentage characteristic operates differently. Ideally, when the plug travel increases by a constant increment, the resulting change in flow rate is a constant percentage of the flow rate at the time of the change. Therefore, when the plug is near the seat, the change in flow rate relative to travel is relatively small, and when the plug is nearly wide open, the change in flow rate relative to travel is relatively large.
I will continue by explaining how the equal percentage characteristic actually behaves and where it is used. A valve with an equal percentage characteristic provides precise throttling control through the lower portion of the travel range, and the capacity increases rapidly as the plug nears the wide open position. Thanks to these characteristics, equal percentage valves are used for pressure control applications. They are also suitable for cases where a large percentage of the pressure drop is absorbed by the system itself, with only a relatively small percentage available at the control valve, and for applications where highly varying pressure drop conditions are expected. In most physical systems, the inlet pressure decreases as the flow rate increases, and an equal percentage characteristic is appropriate for such situations. For this reason, equal percentage is the most commonly used valve characteristic. Meanwhile, Figure 3.30 shows a typical construction for implementing a quick opening characteristic, which you can refer to for comparison with the following characteristics.
Now, I would like to introduce the quick opening flow characteristic. A valve with a quick opening characteristic exhibits the maximum change in flow rate at low travels. The curve is basically linear through the first 40% of plug travel, and after that, it flattens out noticeably, so the flow rate hardly increases even as the travel approaches the wide open position. Because of this characteristic, quick opening valves are often used for on-off applications where a significant flow rate must be established quickly as the valve begins to open. Consequently, they are commonly used in relief valve applications. Additionally, since the quick opening characteristic is linear up to about 70% of the maximum flow rate, quick opening valves can be selected as an alternative for many applications where linear characteristics are recommended.
I will continue by explaining the linearity limits of the quick opening characteristic and the plug guiding methods. The linearity of the quick opening curve drops sharply after the flow area generated by the plug travel equals the flow area of the port. In a typical quick opening valve shown in Figure 3.30, this occurs when the plug travel equals 1/4 of the port diameter. Moving on to plug guiding. Accurately guiding the plug is essential for proper alignment with the seat ring and efficient control of the process fluid. Cage guiding is a method where the outside diameter of the valve plug is kept close to the inside wall surface of the cylindrical cage throughout the travel range. Since the bonnet, cage, and seat ring are self-aligning upon assembly, the alignment of the plug and seat ring is assured when the valve closes, as shown in Figure 3.15. Top guiding is a method of aligning the plug using a single guide bushing in the bonnet or valve body, or by a packing arrangement. Please refer to Figure 3.4.
I will now introduce the remaining 3 plug guiding methods. Stem guiding is a method where a guide bushing in the bonnet acts on the plug stem to align the plug with the seat ring, which corresponds to the left view of Figure 3.3. Top and bottom guiding aligns the plug using guide bushings in both the bonnet and the bottom flange. Please refer to Figure 3.7. Port guiding is a method where the valve body port directly aligns the plug. This construction is typically used in control valves that use small diameter plugs with fluted skirt projections to control low flow rates, as shown in the right view of Figure 3.3.
I would like to introduce restricted capacity trim. Most control valve manufacturers can provide valves with reduced or restricted capacity trim parts. Figure 3.31 shows an adapter method for implementing reduced flow capacity, consisting of a gasket, bonnet, gasket shim, and optional restricted trim. There are several reasons why reducing the flow rate in this way is desirable. First, using restricted capacity trim makes it possible to select a valve body large enough for future increased flow requirements, while sizing the trim capacity properly for present needs. Second, valves can be selected for adequate structural strength while retaining a reasonable travel-to-capacity relationship. Third, large valve bodies with restricted capacity trim can be used to reduce inlet and outlet fluid velocities. Fourth, the purchase of expensive pipeline reducers can be avoided. And finally, oversizing errors can be corrected using restricted capacity trim parts.
This is a method of reducing the flow capacity of a valve using an adapter.
Now I will introduce the restricted trim adapter, or the method for reducing flow capacity. In conventional globe-style valve bodies, capacity is reduced by fitting seat rings with a smaller port size than normal and valve plugs sized to fit those smaller ports. For valves using cage-guided trim, the method is slightly different. The plug, cage, and seat ring parts are taken from a smaller valve size of similar construction. Then, adapter pieces are placed above the cage and below the seat ring to mate these smaller parts with the original valve body. This structure is shown in Figure 3.32. Since reduced capacity service is not unusual, leading manufacturers always keep trim part combinations ready to perform the required function. Please also note that many restricted capacity trim combinations are designed to provide approximately 40% of full-size trim capacity.
Next, we turn to actuator systems.
Next, I would like to introduce actuators. Among the actuators that move a control valve, pneumatic actuators are the most widely used type. However, pneumatic is not the only option. Electric, hydraulic, and manual actuators are also widely used in the field. Therefore, you can select the appropriate drive method according to the application and requirements.
In this chunk, I will introduce the overall types of control valve actuators and the basic operation of pneumatic actuators. Among the actuators used to move control valves, the pneumatic method is the most widely used. Of course, electric, hydraulic, and manual actuators, which are operated by hand, are also widely used. Among pneumatic types, the spring and diaphragm method is most commonly specified because of its high reliability and simple design. Meanwhile, pneumatic piston actuators provide the high stem force required for demanding service conditions. Both spring and diaphragm and pneumatic piston methods have modified versions available, so they can be mounted directly onto rotary shaft control valves.
I will now explain the selection criteria between different types of actuators and the input for diaphragm actuators. The pneumatic actuators mentioned earlier are also available in versions for direct installation on rotary shaft control valves. Electric and electrohydraulic actuators are more complex and more expensive than pneumatic actuators. However, they are advantageous in specific situations. First, where no air supply source is available. Second, where ambient temperatures are low and there is a risk of condensed water freezing in the pneumatic supply lines. And third, where unusually large stem forces are required. Diaphragm actuators use air supplied from sources, such as a controller or positioner as their power source. Figure 3.32 shows direct-acting and reverse-acting diaphragm actuators.
This is the basic structure of a diaphragm actuator that uses pneumatic pressure to drive a valve.
Now, let's summarize the classification of diaphragm actuator operating modes. First, direct-acting actuators push the diaphragm down as air pressure increases, extending the actuator stem. Conversely, reverse-acting actuators push the diaphragm up as air pressure increases, retracting the stem. Both of these operations are shown in Figure 3.32. Reversible actuators can be assembled for either direct or reverse action. An example is the field-reversible multi-spring actuator shown in Figure 3.33. Finally, there are direct-acting units for rotary valves, which operate by pushing the diaphragm down as air pressure increases.
This is a multi-spring type actuator that allows for setting changes in the field.
Here, I will explain the characteristics of diaphragm actuators for rotary use and introduce piston actuators. For direct-acting units for rotary valves, increasing air pressure pushes down on the diaphragm, which may either open or close the valve depending on the orientation of the actuator lever on the valve shaft. This is shown in Figure 3.34. The net output thrust is the difference between the force generated by the diaphragm and the opposing spring force. Molded diaphragms provide linear performance and increased travels. The actuator size is determined by the required output thrust and the available supply air pressure. Diaphragm actuators are simple, dependable, and economical. Moving on, piston actuators often eliminate the need for a supply pressure regulator because they use high-pressure plant air up to 150 sig, and they provide maximum thrust output and fast stroking speeds.
This is a diaphragm actuator for driving rotary shaft valves.
In this chunk, we cover the operating modes and accessories of piston actuators. Piston actuators are either double-acting to provide maximum force in both directions, or spring return to implement fail-open or fail-closed operation if the supply is lost. This is shown in Figure 335. To maintain the position of a double-acting piston when supply pressure is lost, various accessories such as pneumatic trip valves and lockup systems can be attached. Additionally, hydraulic snubbers, hand wheels, and units without yokes are available, which are used to operate industrial equipment such as butterfly valves or louvers. Versions for rotary shaft control valves include a sliding seal in the lower end of the cylinder, which allows the actuator stem to move laterally, as well as up and down without leakage of cylinder pressure.
This is a control valve equipped with a double-acting piston actuator.
I would like to introduce the connection structure of piston actuators applied to rotary shaft control valves. The key to this method is the sliding seal installed at the bottom of the cylinder. Thanks to this seal, the actuator stem can move not only up and down but also laterally, while preventing cylinder pressure from leaking. Since lateral movement is possible, the actuator stem can be connected directly to the lever mounted on the rotary shaft. As a result, one joint that was previously present is eliminated. This joint was originally a point where lost motion occurred. In other words, by removing one connection, the factor that degraded operational precision is eliminated.
I'd like to introduce electrohydraulic actuators. These actuators operate with only two things: electrical power to the motor and an electrical input signal from the controller. They are ideal for isolated locations where pneumatic supply pressure is unavailable, but where precise control of the valve plug position is still required. The direction of operation can be reversed with only minor adjustments. Additionally, they can be configured as self-contained units, housing the motor, pump, and double-acting hydraulically operated piston within a single casing, which is manufactured to be weatherproof or explosion-proof. You can check the related structure in Figure 336.
This is a control valve combined with a double-acting electrohydraulic actuator and a hand wheel for manual operation.
Next, let's look at manual actuators. Manual actuators are useful in places where automatic control is not required, but where ease of operation and a certain degree of accurate manual control are still necessary. A representative example is their frequent use in operating the bypass valve within a 3-valve bypass loop configured around a control valve. This is because the process can be controlled manually through this bypass valve while the automatic system is being maintained or is shut down. The related layout is shown in Figure 337.
These are various types of manual actuators used to operate valves manually.
I will now cover the detailed characteristics of manual actuators and introduce rack and pinion actuators. Manual actuators are available in various sizes for both globe-style valves and rotary shaft valves. Some models are equipped with dial-indicating devices, allowing the valve plug or disc position to be accurately repositioned. In terms of cost, they have the advantage of being much less expensive than automatic actuators. Next, the rack and pinion design is a compact and economical solution for rotary shaft valves. However, because of backlash, the play between gears, they are primarily used for on-off applications or in cases where process variability is not a major concern. The related structure is shown in Figure 338.
This is a rack and pinion actuator, which converts rotary motion into linear motion.
Finally, I'll introduce the basic concept of electric actuators. Traditional electric actuators move the valve by combining an electric motor with some form of gear reduction. By appropriately modifying this mechanism, it has been utilized for continuous control, although the degree of success has varied by case.
Let's discuss the current status and future outlook of electric actuators. As mentioned, while electric mechanisms have been applied to continuous control through adaptation, the level of success has differed across various applications. Furthermore, a clear limitation has been that they were much more expensive than pneumatic actuators when comparing the same performance levels. However, this is a field of very rapid technological change. Therefore, depending on future design advancements, the trend may shift toward an increasing use of electric actuators.
Now, I'd like to introduce representative manual actuators and rack and pinion actuators. Figure 337 presents manual actuators for both sliding stem valves and rotary shaft valves. You can think of manual actuators as a method where a person directly opens and closes the valve using a device such as a handwheel. And Figure 3:38 shows a typical rack and pinion actuator, which is used to drive rotary shaft valves. It is structured to turn the valve shaft by having the rack and pinion gears mesh to convert linear motion into rotary motion.